Now we're getting into a section called phenols. Okay, and phenols are a combination of benzene ring with an alcohol on it. And we've done alcohol chemistry before, and you've done aromatic chemistry before. So it's a combination of both. Phenols are dealt with separately because they have a little bit of unusual chemistry. Let's look at the nomenclature first. This is the phenol as you know it. You also know some of the derivatives of phenol. So for example, this one, which is a methyl group along with the OH group on benzene, these are called crisols. And because the relationship is meta or 1,3, this is called metacrisol. Or in an IUPAC way, you would call it 3-methylphenol. If you have two alcohol groups on the benzene ring, this is called catechol, and that is the unofficial name, the general name for this diol. The official name would be 1,2-benzene diol. 1,4-benzene diol would be called hydroquinone. There's another one called resorcinol, which is the meta diol. Okay, and so there are three kinds of diols possible. These diols have a little bit different properties. Okay, and so for example, we'll talk a little bit about hydroquinone towards the end, but these are some of the derivatives. One of the properties of alcohols that we know of back from the alcohol chapter is the acidity of alcohols. And so since phenols are also alcohols, we have to talk about the acidity of phenols. And so here is the alcohol group, okay? And you saw that before also. And so this hydrogen, which is attached to the oxygen, is the acidic proton. So phenols are also acidic, and alcohols in general are also acidic. However, phenols are more acidic than alcohols are. Okay, and so we have to find out why they're actually more acidic, and that has to do with the fact that you form this ion, which is called a phenoxide ion. When you have a regular alcohol, an aliphatic alcohol, and then you form an alkoxide ion, okay, that is called an alkoxide ion. It has different properties. However, this phenoxide ion has a little bit different properties. And why so is because this oxide is connected to the benzene ring. And because it's connected to the benzene ring, it can actually undergo resonance, which means that the electrons on this oxygen are delocalized all over the benzene ring. So if they're delocalized all over the benzene ring, it means that this ion is very stable. If this ion is very stable, it makes phenol a very good acid. Okay, so the proton stays in solution. It doesn't have a need to come back to the oxide. And so phenoxides actually are very good or phenols, I should say, are very good acids. And phenoxide is a very stable ion. And because of that, it actually has some very unique properties. Okay, but we'll talk about that also. Let's finish off a little bit more about the acidity of phenols. So here are some phenol derivatives, okay? And so how can you change the acidity of phenols? The interesting thing about alcohols was that yes, you can change the acidity of normal alcohols too, and you can also change the acidity of phenols as well, okay? So for example, here is phenol with a pKa of 9.95. However, if you have a nitro group on it, then the pKa goes further down, okay? And then here's another nitro group and pKa goes further down. Okay, and so this one here is a para position to OH, so it's directly opposite. Okay, and so therefore it has even more of a stronger effect than if it was a meta nitro group. Okay, and so if you have any other electron withdrawing group on the benzene ring, it will make the phenol even a stronger base. Okay, excuse me, a stronger acid. If you have electron donating groups, okay, for example, like the methyl group is an electron donating group. So if you have electron donating groups, then the pK will become higher than phenol. So here is a little nice comparison of all the different kinds of pKs. So here's phenol with 9.95, but a methyl group makes it 10.01 and chlorine makes it 8.85 because chlorine is electron withdrawing, whereas the methyl group is electron donating group. Okay, and so you can change the acidity power of your phenol. Again, here the nitro group is just showing how the resonance is taking place. Okay, and you should be able to write out all these resonance structures. So this just shows the delocalization, okay, and how the nitro group is also participating in the delocalization, which is what makes the para nitrophenol very strong acid, okay, because it is also participating in the resonance. When it's meta, it's not participating in the resonance, okay. Here is another list of pKa's, and this is a nice one because it compares the phenols with some other alcohols, okay, also. And so here is paranitrophenol, very acidic, and then here are some of the other alcohols, okay. And so it's a good handy table to have in case you're trying to compare and understand what makes an acid a good acid. So you look at the substituents and then you figure it out. Phenol can be made in the industry. It's a very common starting material. Phenol is very common, and so which means that it is made industrially. Okay, and so in the industry, it's made from cumene, and cumene is isopropylbenzene. Okay, the structure is right here, and you oxidize that, and it gives this kind of a peroxide. And once this peroxide is treated with acid, you get phenol, and you also get acetone. One of the things that industries try to do is maximize everything, their processes, so that there is no wastage. And this is a really cool process because there is hardly any waste in there, and you need minimum amount of chemicals. Okay, and so you end up getting phenol, and you also get acetone, which is another one of those very common chemicals that we use. So where do we really find phenols? Phenols are found everywhere, okay? A lot of the phenols are going to be antiseptic, just like alcohols are. You've also dealt with eugenol in your lab. Eugenol is a dental antiseptic and analgesic you can use for dental pain. And here is eugenol. This is what you isolated from cloves, okay? It's a very common, very nice smelling compound. And a lot of phenols actually are very nice smelling compounds. Urushiol is component of oil of poison ivy, which I don't think is in any sort of a disinfectant, okay? But however, this is also a place where you would find phenols. Here are quinones in nature, and this is what I was talking about before, where hydroquinone becomes very important, okay? And quinones are very well known for transporting electrons. Okay, so they are really involved in our body in the nature as electron transfer process systems. Okay, and so here is hydroquinone. Okay, and here is what we call quinone. Okay, quinone is an oxidized form, and hydroquinone is the reduced form because you have the hydrogens on there. And so what it does, it helps in the electron transfer process. Once you really get into the basics of how oxidation and reduction occurs in our body, then you get to the electron system and the electron transfer. Once you get into the electron transfer, that's when you use this NADH, okay, which is an enzyme. And so this enzyme is really used in citric acid cycles where you have the oxidation process taking place. So if oxidation is occurring, then NADH gets reduced. So in order for NADH to become oxidized again, then these quinones will actually take part in that process. Okay, and so that's why you find quinones in a lot of our electron transport processes. So the reactions of phenols, there are few reactions of phenols, and some of them are really unique. A lot of them are just like alcohols. Okay, so the first one, which is really interesting one, of course, is the formation of hydroquinone, okay, or benzoquinone in this case. Hydroquinone would be the two alcohols, but this is benzoquinone. And so you can take a phenol and oxidize it, okay, to give benzoquinone. Again, these are highly oxidized systems. And remember, the hydroxyl group is a very strongly activating groups, and phenols, as we talked about before also, it really activates the benzene ring, and so it makes it easy for you to do halogenation, nitration, and all sorts of wonderful reactions on the benzene ring, sometimes even without a catalyst. So ethers, as you know how to make before also, okay, is you take an alcohol, you make an alkoxide out of it. In this case, it's a phenoxide, and then you treat that with any kind of a substrate with a leaving group, and you get a normal SN2 reaction, and you form an ether. This is anisole, and so or methylphenyl ether. Okay, and so you can form ethers. One of the most interesting synthesis is Kolbe synthesis, and depending on which textbook you're using, it may or may not be in your textbook, but I would like to include the synthesis because it's really very interesting. And it's also a very common synthesis of salicylic acid, okay, which is aspirin. So here's phenol, and you treat that with a base normally and you get phenoxide. Now the benzene ring is so activated at this point that it reacts even with carbon dioxide, okay, to give a carboxylate ion. And once that is protonated with a weak acid, it ends up giving salicylic acid, okay, or it gives the carboxylic acid over here now, and the phenol group is still there because the reaction actually was not of the alcohol group. The reaction here was on the benzene ring, okay. And so this is coal-based synthesis, and it's a really very efficient synthesis. And one of the things that you will see in this synthesis, it's again, there are not very many chemicals involved: sodium hydroxide, carbon dioxide, and HCl. Okay, very simple synthesis, but again, this is only because the phenoxide ion is so activated that it can actually start doing reactions on the ortho position with even carbon dioxide. So a very small topic here, okay, regarding the phenols. Please know the nomenclature of phenols. The acidity of phenols is a very common question that you get. And then, of course, the two syntheses that we talked about and the oxidation. So in case you are asked that anywhere, you should know that how you can form hydroquinone from quinones. That's about it.